Hello and welcome to another Ginger Mathematician video where I'm going to go through all things you need to know for A-Level Maths Paper 1, the 9709 course on radian measure. So everything you need to know, and we're going to get through lots of exam questions in this long video today. So first of all, what is a radian? So you might have heard this word before. What is it? Essentially, it is a much better way, basically, or more mathematically natural way to measure an angle. So we consider this angle here to be 1 rad, so 1 rad unit, and that is when the radius is equal to the arc length. In fact, in German, we use the word Bogenmaß, which translates literally as bow measure or arc measure. So literally the measure of the arc. And 1 unit of this radians is equal when the radius is equal to the length of the arc. Now, from this definition, you can then convert between radians and degrees. And this very strange definition comes out here, which is 1 radian is equal to 360 over 2 pi degrees. Let me just show you very briefly where that comes from. So if I say that 1 rad is equal to, say, x, for example, well, let's think about the arc length formula that we learnt from IGCSE. Well, the arc length in our diagram here is just equal to r, and it's also equal to the angle, which is x in this case. This is going to be in degrees here, over 360, and then times the formula for the circumference of a circle, which is equal to 2 pi r. At this point, all we do is rearrange this to make x the subject. So we times by 360, so we get 360r is equal to x degrees times 2 pi r. Then we divide through by 2 pi r, so we get 360r divided by 2 pi r is equal to x degrees. And we have r top and bottom, so we can cancel. And notice that then x degrees is equal to 360 over 2 pi radians. So this is where this definition comes from. Again, not needed for the actual exam itself, but if you're interested where this comes from, this is kind of a quick demonstration why. Now, luckily, most of the time you don't really have to use this conversion a lot. We're going to use what's called standard degrees, so 180, 360, 270 and so on, and it fits very, very nicely into radians. So the example here, for example, if I have pi radians and I want to convert to degrees, I just times by 360 over 2 pi. This cancels here. 360 divided by 2 is 180 degrees. So 180 degrees is the same as pi radians. So if you look at my table here, I'm going to put 180 like so. If I take 135 degrees, if I want to convert that, then we obviously divide by it instead, so working backwards. But this is equal to 3 pi over 8, so I can pop this in my table. And it's a very good exercise for you to do at home. I'm not going to go through this in a particular video, to work out the main conversions you need to know from degrees to radians. For example, if I know 180 degrees is pi radians, what do I do to 180? To get to 90, well, I divide by 2. So then I do the same with the pi. Pi divided by 2 is just pi over 2. And then 45, same relationship here. What do I do to 90 to get to 45? I divide by 2. So I do the same thing again. And pi over 2 divided by 2 is pi over 4. So if you know these off by heart, these particular values here, and notice there is a pattern, if you've noticed it already. It's actually going up in 15 degrees, because 15 degrees is equal to pi over 12, and then you can work out the exact values here. These tend to be very, very useful, and I'll be using these throughout the video, so it is worth learning off by heart. Now, the reason we actually work with radians rather than degrees, it makes our life a lot easier when we're working with arc lengths, arc sectors, and the area of segments as well, which I'll talk about later. So have a think at home just for a few seconds. What do you know about circles to work out the arc length and the area of the sector? I've already given you one of these formulae already in the video. Now, hopefully you remember the arc length from IGCSE is equal to the angle divided by 360 times the circumference of the circle, so 2 pi r. Area of sector works in almost a very, very identical way. We have angle divided by 360 times the area of a circle, which is pi r squared. Now, if we use our definition here, that we looked at before, which is that 1 radian is equal to 360 over 2 pi degrees, and rearrange this slightly by timesing by 2 pi on both sides, then 360 degrees is equal to 2 pi radians, an important exact value you need to know. Now if I substitute this into my formula, so we go from the angle in degrees to the angle in radians, so wherever I see a 360, I'm going to replace it with 2 pi. At this point, the 2 pi's cancel here, and then we have the formula in radians. This is important here. So when we look at the calculator later, must be in radians. Our arc length is now a really, really easy formula. It's just the angle in radians times the radius. That actually gives us here the arc length S. A similar simplification happens for the area of a sector. So wherever we see a 360, we replace it with a 2 pi. We get some cancellation here, so we get a pi cancellation. And then we end up with the formula of a half theta r squared for the area of the sector. But again, this angle has to be in radians in order to use the formula, and make sure your calculator is in that as well. So if I give you a couple of questions just to warm up, and then we're going to look at some exam questions. So the arc AB subtends an angle pi over 3 at the center of a circle radius 6 centimeters. So let me just draw this out like so. So we have pi over 3, and we have a radius of 6 centimeters. Find the length of the arc, let's call that x, and then the area we'll do later. So remember, the arc length here using the formula is just the angle in radians, which it is here. So pi over 3 times the radius, which is 6, and that then just gives us 2 pi centimeters. Remember, this is a length that we're looking for. The area we can work out in a very similar way. We use our formula, so a half theta r squared. Doing all this in exact values, again, you can check on your calculator. So we have a half times the angle in radians, which is pi over 3 times the radius squared, 6 squared. So that gives us then pi times 36 divided by 6. And if we simplify that down, that just gives us 6 pi centimeters squared. Hopefully this particular example shows you how easy it is just to work out areas and arc lengths very, very straightforwardly. Something a bit more problem solving here is this question here. So we've got the perimeter of a sector of a circle. So let's draw in our sector like so. Radius is 3 and 3 here. And the perimeter is equal to 8. So 3 plus 3 is 6. So then this arc length must be equal to 2 centimeters because it all adds up to 8. Find the area of the sector. So we're going to work backwards here because the arc length formula is equal to r theta, where it's in radians. The arc is 2. The radius is 3. So we get 2 equals 3 theta. Therefore, theta is equal to 2 over 3 radians. Now you can use this symbol here for radians. It looks like a C, but actually what it's doing is representing an arc. Remember that Borgenmass thing I said earlier on. So this here, it looks like a C, but actually it's just representing a small arc. This is our angle here, and now we can work out the area. So our area formula is a half theta r squared when theta is in radians. So we get a half times 2/3 for the angle times the radius squared, which is 9. 3 squared is 9. If we simplify this down, what do we get here? So 2 times 9 is 18. 18 divided by 6, and that's equal to 3 square centimeters, like so. So I just went through a couple of easier examples before we start on the exam questions, just to show you the benefit of working in radians. I haven't even touched the calculator at this particular point, and just shows the effectiveness of when you have the angle in radians, the formula become very, very easy to manipulate. Right, so before I move on to the actual exam questions, just a reminder about the formula sheet that you get for A-Level Maths Paper 1 and the other A-Level papers too. So the formula we'll be using most of the time are the ones I've introduced here. However, there is one that's not on the formula sheet that could be useful for you, and that is to find the area of the segment of a circle. So what I mean by this, say I have my sector here, and I want to work out this area, then this formula directly will just work out the area of the segment for you. Of course, you could just use the area of a triangle, area of a sector, take one away from the other. But again, if you want to save time in that paper 1 exam, and I know time is tight in that exam, then you do want to be using this formula. It will just save you some time. But again, be aware it's not on the formula sheet for you. Right, let's carry on. So we've got some exam questions here, all from the last couple of years. So I'm trying to keep it as up to date as possible. So the diagram shows a sector OAB with centre O. The length of the arc, as we're given, is 8 centimetres. It is given that the perimeter, very similar to our example, of the sector is equal to 20 centimetres. Find the perimeter of the shaded segment. So watch out for that. So we want the perimeter of this shape here. Now it is 4 marks, so it's going to involve some working here. However, we know the whole perimeter of the sector is 20. So 20 minus 8 is equal to 12. So these two have to add up to 12. So each one here must be equal to 6 centimetres in order for that to be true. Now, generally in these kind of radian questions, you're going to have to try and find the angle out at some point. And this is where we can use the arc formula. Remember, our arc formula is equal to r theta, where theta is in radians. Now we know the arc is equal to 8. We know the radius is equal to 6, so we get 8 is equal to 6 theta. Therefore, quick rearrangement here. Theta is equal to 8 over 6, and that's equal to 4 over 3. Now, if you forget about radians, you can always keep putting in this small c. That's just going to help you and remind you you need to be using radians later on. So this is equal to 4/3 c. And at this point, we're looking for the perimeter, so we have to be careful with that. So we need to work out this side here. And this is where your IGCSE skills come in very, very useful. Because essentially we have a non-right angled triangle. We have two of the smaller sides looking for the longer side. This is going to call for the cosine rule. Now remember, the cosine rule is c squared equals a squared plus b squared minus 2ab cos c. If you've forgotten everything about the sine and cosine rule, then do check out the video above, because I go through the IGCSE skills that you need to be able to do this. Again, this is a radian video, so I'm going to go through this relatively quickly. So let's label our sides here. So these will be the two smaller sides, A and B. This is our longer side, C. This is the big angle, big C. So we can use this now to work out this small c here. So I try and keep this in one smooth calculation. Notice I could write c on its own here by just square rooting both sides. So I do not want to waste time or space in the exam, so I'm going to be writing this in. So small c here is equal to the square root of 6 squared plus 6 squared minus 2 times 6 times 6. Now remember, the cosine is in radians, so make sure when we go to our calculator in a moment, this is in radians, otherwise you'll get the wrong answer. So, talking about that, let's go to the calculator and work it out. Okay, so what we need to do, I'm going to use the CG50 here. Again, this is a bit overkill for the A-level exam, but I'm kind of used to it at this point. And it has the standard functions a Casio kind of does. So we have shift, we've got 6 squared. So just being very careful how we pop this in. Now notice it says rads at the top. If you need to change it, you go to shift setup if we need to change that. So 2 times 6 times 6 times cosine. And we'll go here. And it was 4/3. So 4 over 3. Close bracket, and we get our answer as 7.4204. Now the key thing is not to round it straight away here. 4204 dot dot dot. And now we want to work out the perimeter here, so we need to add on the 8 here. So we take on our 7.4204, representing the C here, add on the 8. Again, we can just go back to the calculator quickly. Again, using the answer feature here, which is really useful. So you go shift and down here, answer plus 8. Get our final answer of 15.4. to 1 decimal place. Generally, rounding to 1 decimal place or 3 significant figures is absolutely fine, and making sure we put in centimeters as well. Perfect. That gets us the 4 marks here. On to the question B, again very common here, area of the shaded segment. This is why if you have that formula to hand and know it, it can just save you a ton of time. So to remind you here, we're going to use this formula here, half r squared theta minus sine theta, everything in radians please, so we get a half. Now the radius equal to 6, so half times 6 squared. The angle was 4/3 in radians, minus sine 4/3. And all we do at this point is just use the calculator. Okay, so we go half, or 0.5, times 6 squared, open brackets, we have 4/3 minus sine 4/3, close brackets, everything correct. You always do a double check before you pop this in, and you get our answer of 6.505. Dot, 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 and we'll round this 6.51 to 3 significant figures, and then our units is square centimeters. So again, 2 mark question. You don't want to spend too much time on this in the exam, so if you know this formula, it's going to save you a ton of time. So you can check what we've just done here. So again, we've taken this kind of approach, again with the shortened version by using the formula, and you can check where you picked up all the method marks and base marks and accuracy marks as well. Okay, and let's have a look at question 10 here. So we've got a diagram and it shows the cross section of the body of an aircraft, and it consists of 2 separate sectors. So first of all, we've got the sector OARB. So let me, again, very, very important then, we're going to label this up. Again, my pen skills not as good as if we're actually on paper here. So if I just draw this in, so this is our first sector we're going to consider in red, and that's got a radius of 2.5 meters, which is given with center O. And then we've also got a sector PASB. So again, I'm going to mark that in a slightly different color, just so we can see these are 2 different sectors we are considering. And to make the body of the aircraft, they are combined together. So we've got this sector with a radius of 2.24 meters at center P, and we've got a sector at the top here at center O. Now the angles are given, so we've got 2/3 pi as AOB and angle APB as 5/6 pi. And our first task here is going to be finding the perimeter, underline the key language here, of the cross section RASB, giving answers correct to 2 decimal places. So notice we've got 2 separate sectors here, so we can approach this one at a time. However, be very careful with the red sector, because when we actually want to look at the angle, we always need the angle inside the shape. Now remember, just a quick reminder, 2 pi radians is equal to 360 degrees. So if we want to work out this angle here, well, 2 pi, if we unsimplify this, we get then 6 pi over 3, which is also equal to 360 degrees. Therefore, this angle here, to add up to 2 pi radians, we need to have this at 4 pi over 3 radians. Notice with the blue sector here, we've actually got the angle inside, so we can use that directly. Now remember to work out the arc, and we'll start with arc OARB. Remember, our formula is just r theta, so it's just 2.5 times 4 pi over 3 for this one here. And then if I do this in a different color here, let's pop this in blue. So the arc of the PASB, again, it's also the same formula, just r theta. So that's going to be 2.24 times 5 over 6 pi. So if we want to work out the total here, we're just going to add those two things together because the perimeter of the shape, remember the outside of the shape, is represented by this interesting red line I've done all the way around and the blue going outside as well. So we just need to add together the two arcs, so 2.5 times 4 pi over 3 plus 2.24 times 5 over 6 pi, or 5 pi over 6, both exactly the same thing. Again, I'm going to tell you this every single time. Make sure your calculator is in the right setting. It is in radians. So we're going to type this in. So 2.5 times 4 pi divided by 3 plus 2.24 times, and we've got 5 pi over 6. Add that together. Now notice your calculator generally does give you an exact answer here of 26 pi over 5, which I think would give you all 3 marks here, but it does say to 2 decimal places, so do press that SD button, and then we get our final answer here of 16.34, again rounding to what they've told you here, which is 2 decimal places. So always be careful, read that question carefully, making sure we guarantee we get all those 3 marks. So if we go on to part B here, now we need to find the difference in area of the 2 triangles AOB and APB, again giving our answer again to 2 decimal places. So if we go back to this, we've got 2 triangles here. Okay, let's get more colours out here. Why not? Let's get colours out like this. So this is AOB, and then we've got the smaller triangle inside. Now remember the formula to work out the area of a triangle. So quick reminder here. So the area of a triangle is equal to half AB sine C. Now you can still use this formula, just make sure again your calculator is in radians. So what we're going to do here, we're going to work out AOB and we're going to work out APB and the area of both of those. So if we start with the bigger triangle here, it's going to be a half times 2.5 times 2.5 times the sine of the angle, so the sine in radians of 2/3 pi. If you want to write the radian sign there to remind you, that can be quite helpful. APB, if we go back to the smaller one here, we have a half times 2.24 times sine of the angle, which I think is 5 over 6 pi in radians, and we want to find the difference here. So the difference between them is just going to be one minus the other. And again, this is where our calculator comes into play, and we're just going to write all this in, making sure of course it is in radians. So let's pop it in. So 0.5 times 2.5 times 2.5 times sine of fraction button 2 pi over 3 and minus, and it doesn't matter which way around we do it anyway because we're going to take the absolute value, but this should give us a positive answer, times the sine fraction button 5 pi over 6 and press the equals button. It takes a little bit of time to load, and that gives us the difference of 1.4519. And again, we want this to 2 decimal places. It's going to be 1.45. Again, strictly speaking, we've probably put this in meters as well. So let's pop that in. Now, what's very typical in A-level maths questions or IB maths questions is often you need to use something you've already done to help you with the following question. And this one is not a surprise, it works in the same way. Okay, so now we want to work out the area of the entire cross section, and we can actually use part B to help us with this. Again, this time we need to give our answer correct to 1 decimal place. So our strategy here is as follows. So notice here I've shaded in the red sector up here. Notice we've got the blue sector we considered before. Notice the bit that's extra we actually worked out in part B. So all we need to do here to work out the area of the entire shape is the area of the red sector plus the area of the blue sector plus that extra area that we worked out in part B. So let's structure this helpfully. So we've got the area of the red part. So that's going to be equal to a half r squared theta. So a half times 2.5 squared times 4 pi over 3. And then we've got the area of the blue part. So just being careful. So we've got half times 2.24 squared times 5 pi over 6. So let's pop that in. So 2.24 squared times 5 pi over 6. And so to work out the total area, we need to then work out the red area plus the blue area plus the area that we worked out in part B. So we can use the non-rounded version here, the 1.4519. And at this point, it's now just being very careful with our calculator and making sure we put everything in clearly. So we've got 1.4519 plus 0.5 times 2.5 squared times 4 pi over 3, and then adding on 0.5 times 2.24 squared times fraction button 5 pi over 6. Pop into our calculator, then here do its stuff, and then we get 21.109. Again, reading the features here very carefully, so one decimal place, so we want 21.1 and we want square meters. Notice we're looking for area and we're working in meters in this particular question. Okay, so you can see the mark scheme there. You can see where you pick up all those method marks as well, getting a very typical 8-mark question on radian measure for paper 1. Right, on to our next question here. So again, question 8, so one of the more difficult questions on the paper. And notice we've got two identical circles, and that's very important here. So both have the same radius, which we're going to name as R. And they intersect at A and B here that are given on the diagram. The radius, yeah, as I said, is equal to R. And the distance between P and Q is equal to 5/3 R. Okay. And the first thing we need to do for 4 marks is find the perimeter of the shaded region in terms of R. So we want to find this length here that I've put in red, but also this length here, which is identical in blue here. So what I'm going to do is I'm going to focus on the red length for the time being, and whatever answer I get for that, I can just double then to work out the perimeter of the whole thing. So imagine I've got another radius here. So notice if I go from P to B, that's also going to be equal to R, because it's just the radius of the circle. And consider if I actually drew a line down here. So this classic drop a perpendicular, I seem to say it in lots of different questions. You're probably wondering why we would want to do this. It's because we've actually got enough information from this triangle to actually work out the angle actually made at P. So the radius here is equal to the hypotenuse of this triangle. However, notice this length down the bottom, the entire length across is 5/3 R. So this length must be half of that, so that's going to be 5/6 R. Remember, 5/3 divided by 2, that's equal to 5/6. So that's why I've taken this specific triangle, because it then allows me to actually work out this angle here. Now, I am going to work in radians here. It's going to make my life a bit easier a bit later in the question. At this point, we're going to use some standard SOHCAHTOA, as we like to call it. So we have the adjacent side, the hypotenuse, why IGCSE is so important. We're going to be using cosine here. So the cosine of the angle, so cos of theta, I'm going to work in radians for this one, is equal to A over H. So it's equal to 5/6 R divided by R. Notice by doing this we can actually just cancel out the R's here. So we get then the cos theta is equal to 5, 6. That's why we can actually work this out. So if we would do the opposite of cos, that's going to be inverse cosine. So theta is going to be the inverse cosine of 5 over 6. Again, we're going to keep this in radians, as I said earlier. So we get cosine inverse 5 over 6. That's going to give us 0. I'm going to keep this in my calculator. 5856 dot dot dot. So that gives me this angle here, which is helpful. So if I double that angle, that will give me the angle of the entire sector I'm focusing on. So if I times that by 2 here, the angle in radians is going to be approximately 1.1713 dot dot dot. And now we can actually use the standard formula for the arc. So if we want to work out the perimeter, it's going to be 2 lots of the arc, because we want this arc and this arc here. So remember, to work out the arc here, it's just r theta when we're working in radians. So it's going to be r times the angle I've marked, which is 1.173 dot dot dot. So we're just going to take that number and then times it by 2. Again, that gives us then 2.34r, and that gives us all 4 marks here. Again, I think you can write this also as exact value, but I think working in decimals is a bit more sensible. So on to question B here, and this is very typical. Now we want to work out the area of the shaded region in terms of r. So this is a bit trickier, but we can make this a bit easier for ourselves by using what we already know. Remember the area of the segment formula. So I gave you this right at the start of this video. Again, if I go back briefly just to show you where I showed you this, this is when we looked at the formula sheet. The area of a segment is actually equal to half r squared theta minus sine theta. So we are going to use that formula, and that's going to help us a bit later on. So just write it down. Area of segment is equal to half r squared theta minus sine theta. Hence why we're working in radians as well, because it's the radian formula. So with that in mind, if we take then the entire shape here, remember these identical circles here, if I draw a line all the way down, notice these 2 segments are equal. So notice this segment is the same as this segment because they're identical circles. So all we need to do to work out the area of what we're looking for, the area of shaded, is do 2 lots of this formula here. So 2 lots of half r squared and then theta minus sine theta. So if we go back, we worked out theta already. So this is the 1.1713. So 1.1713 minus the sine. Then should be dot dot dot. Sine 1.1713. Again, at this point, we can actually simplify this fairly straightforwardly. This cancels, so we're just going to get an r squared here. Then we just work out what's inside the bracket. So if we take that, we get 1.713 answer minus sine answer. And that then gives us 0.2500. It was good to show this just so we can round it afterwards, and that gives us then 0.250 r squared for our 3 marks. I think there are other approaches of taking here, but as I said to you earlier in the video, knowing the area of the segment formula is really, really helpful because it can speed up a lot of these more tricky questions towards the end, giving you more time in the exam. So you can see the 2 answers here. Again, I think they've worked out slightly differently for part B, but the area of the segment, it's more important than you think. Okay, and on to this question 5. So using a fair bit of trigonometry here at the same time. So we've got a sector ABC with centre A and radius R. Line BD is perpendicular, which we are given here, and CAB is in radians, which is important. And we're actually told for the first part of the question that theta is equal to pi over 6. And from that, we need to work out the exact area, so no relying on our calculator here, for BCD in terms of R. Now, whenever you get a kind of a weird shape you're looking for the area for, try and use a sort of general sector and take things away from it. So our strategy here is going to be sector, so the area of the entire sector, and then minus the triangle. So strategy in my head. Before I even start the question, let's see what we can do. So the first thing is the area of a sector. I think that's fairly straightforward here, because that's just a half r squared theta. So in terms of r, so a half r squared, and this can be timesing theta here, so that's times pi over 6. And if we simplify this down, we get then pi over 12 r squared. Perfect. So we've done the whole sector. Now we need to look at the triangle. This is where a little bit of trigonometry comes in. So to work out the area of this triangle, we need to use a half base times height, or we could do a half AB sine C as well. I think I'm going to go down the base times height route here. So first of all, we need to find what AD and DB are. So to do that, we need to use sine and cosine. Notice this is the adjacent, this is the opposite, this is the hypotenuse. So that means that sine of the angle, so sine pi over 6, is equal to O, so dB here, over h, which is r. So therefore dB is going to be equal to r sine pi over 6. Now hopefully you know the exact value, but again you could always check this on the calculator as well. So this is going to be a half r. So pi over 6 is the same as sine 30. Sine 30 is equal to a half, and we can do a very similar process here. So let me write this down here. So cos pi over 6, that's equal to AD over R. So similar kind of calculation here. AD is equal to R cos pi over 6. Again, you should know these exact values. This is why, again, IGCSE is useful. So cos 30, that's equal to root 3 over 2. So we get root 3 over 2r. So to work out the exact area, we have the area of the sector, which we worked out before, the whole thing, and then we're going to take away the area of the triangle. So that's going to be a half times base, which is root 3 over 2r, times the height, which is equal to a half r, and so that's going to give us pi over 12 r squared. The denominator, that will become 8. The top is just going to be root 3, and r times r is r squared. So we can leave it in that form. Again, you could always factorize this if you want to show off to the examiner and do r squared, open brackets, pi over 12 minus root 3 over 8. That is also fine. Okay, part B is a nice little twist, as they like to do with these part Bs. So given instead that the length of BD is root 3 over 2r. So imagine I take everything here, I erase all the ink, there it goes, and we're just told now that BD is equal to root 3 over 2r, and this time we want to find the exact perimeter of BCD, so this shape here, in terms of r, I assume. Yeah. So first thought is we need to find this angle one way or the other. We can use trigonometry. Again, this is still the opposite and still the hypotenuse. So sine of the angle, which we're going to write in radians here, is equal to opposite, so root 3 over 2r divided by r. The r's cancel, which is very helpful, giving us then that sine theta is equal to root 3 over 2. Again, if you do forget your exact values, that's absolutely fine. Work out the inverse sine here of root 3 over 2. But again, you can always put your calculator in radians, then you just go sine inverse root 3 divided by 2. And notice it will give you then 1/3 pi or pi over 3. So again, if you forget them, get panicky in the exam, again, your calculator is there to help you. So we've got this now as pi over 3. So now we just can work out each of the different lengths here. We've already got BD, but to work out BC, that's just the arc of the sector. So this is r times theta. It's going to be r times pi over 3, which is pi over 3r. So we now know what that is. This is why radians are so powerful. The slightly trickier part here is working out the DC. Well, notice going all the way across this part here, that's going to be equal to the radius, because AC is part of the sector, the radius of the sector. So to work out AD, again, we can use a little bit of trigonometry here. So cosine pi over 3 is equal to A, so AD, all divided by R. So quick rearrangement. Again, if you can go straight to the answer here, that's absolutely fine, but just to show my steps. And cos pi over 3, again cos 60, it's one you need to know, that's equal to a half, so you get a half R. So this is not particularly well to scale here. So if that means then the whole thing is R, and AD is equal to a half R, this must also be equal to a half R as well. So if we want the perimeter here, we just need to add all these things together. So the perimeter will be equal to a half R plus root 3 over 2R plus pi over 3R. We're just adding the three sides of the shape that we are looking for there as well. Again, any order is also fine too. So you can have a quick look through the mark scheme and make sure you're just happy with what I've done there. Again, you can rely on your calculator to work out some of these exact values for you. Okay, and on to question 7, which is quite similar in some respects to the previous question, but a bit more calculator work. So again, we've got a sector OBAC with our centre at 0, radius of 10. The point P lies on OC and BP is perpendicular to OC. So we've got this dropping perpendicular already. AOC, this angle here is equal to 1/6 pi, and the arc is equal to 2. And we want to find the entire angle BOC, so this entire angle here. So before we can do that, we need to find this small angle here. And this is just a nice rearrangement of arc is equal to r theta. Well, the arc for this very small part here is equal to 2. So we get 2 is equal to 10 times theta. We're working radians here. So that means just divide both sides by 10. That's this angle equal to 1/5 in radians. So if you want the entire angle here, so the entire angle BOC, that's going to be equal to 1/5 plus pi over 6. So these two angles added together. Again, 2-mark question, it shouldn't be anything too difficult. However, we are going to have to use that answer. So let me just pop that in. So this entire angle is 1/5 plus pi over 6 for the next part of the question. Now we've got that magic word hence. I've talked about this in this video and other videos before. So we are using part A in some way, which is really important. And we want to find the area of the shaded region BPC, so this region here. And we want the answer, so no exact values here, to 3 significant figures. So again, same strategy as before. We want sector minus triangle. I'm going to take a slightly different approach to what I did before. However, we still need to write down the area of the sector. That's going to be equal a half times 10 squared, so half r squared, times theta. Remember, the whole angle here is what we worked out in part A. So it's going to be 1/5 times pi over 6, sorry, plus pi over 6. Quickly erase that. So we can simplify this down slightly. So 10 squared is 100. 100 divided by 2 is 50. So again, we can write it like so. We could even multiply through as well, but I'll leave it like this for the time being. I think that is fine. Now we need to focus on the triangle. So I'm going to take a different approach to what I did in the previous one. I'm going to start using a half AB sine C. Well, the point of this video is to try and show you lots of different ways of approaching the same thing. And by seeing these and seeing these in action, hopefully one of these ideas will then stick and make sense to you. So in order to use a half AB sine C, we need to work out the side OP here. Again, we have the adjacent and hypotenuse. So we can then say the following, that the cosine of the angle, which is this 1/5 plus pi over 6, is equal to adjacent, which is what we're looking for, OP, divided by the hypotenuse, that's equal to 10. So times by 10 on both sides. This again gives us an expression So let me just write that down here. And let's just get a decimal approximation for this. So 10 cos 1/5 plus pi over 6. And put the bracket in the wrong place, which is never something to do. There we are. So we get 7.49427 dot dot dot, which I'm going to label on my diagram. So 7.49 dot dot dot. And now I've got this side and the angle in between. To work out the area of the triangle, we can then just do a half times what I just worked out on the calculator, times 10 times the sine of the angle in between. So again, using part A here, it's important to keep in mind. So if we pop that in, we get 5 times 10 times sine of the angle. Hopefully by this point in the video, it's now feeling much more comfortable what kind of questions can appear. And that gives us then 24.809 dot dot dot. And so to work out the region that we're looking for, following the strategy we mentioned earlier, is we're going to take the 50 1/5 plus a pi over 6 and then minus the 24.809. I'm using the answer key quite a bit on the calculator, avoiding those rounding errors, which is really, really crucial. So 1/5 plus pi over 6 minus the answer we just made. That then gives us 11.3706. This time, notice I keep changing the rounding, so you've got to keep aware of this. So 3 significant figures, that's going to be 11.4, working in centimeters, so centimeters squared. It's all about attention to detail, making sure we get the precise answer that we are looking for. Okay, so that's the answer for the first one here. So question 7a, they wrote 0.2, but 1/5 is also fine. And then you'll see the answer right at the bottom here. So the rounded answer we're looking for is 11.4. So hopefully this has really got you up to speed on all things you need to know radian measure. Again, check out the video right in front of you if you want to do all things binomial expansion. Again, that's also a very important topic that you need to know and master to make sure you do really well on paper 1.